Hey, what up, guys? Welcome back. This is going to be likely the last critical installment in this OpenGL stuff for CS-330. I might do some supplementary stuff afterwards, but for now, this will cover everything you need to do for pretty much all your assignments up until the end of week 7, and week 8 is kind of, if I recall correctly, just modifying something that already exists. So what we did last week is we implemented textures and how to get the textures working on our objects. What we're going to do this week is we're going to put basic lighting. It's called the Phong shading model, where I think it's specular, diffuse, and ambient lighting. So that's what we're going to do this week. We're going to start off, first I'm going to show you how to turn off backface, or how to turn on backface culling, which means it doesn't draw the backside of your faces, which will be important so that you can verify that all of your triangles are facing the same direction. And once your triangles are facing the same direction, we can use some code to properly calculate the normals of each one of your objects, so that these objects normals will be pointed in the right direction, so that when the light is calculated, that everything looks good. So that's our plan for today. Again, join us on our Discord. We're all there to help you whenever you need it, but let's just get into this. I'll try to make this a little bit shorter this week, but we'll see how it goes. I've been saying that for weeks. All right, so just to go off what I was saying in the intro, these are going to be the 3 lighting models that we're going to be implementing today. So the first one is called ambient lighting, which is the base level of lighting present in your scene. So imagine, so think of it kind of like the sun. If without a direction, like when the sun is out, everywhere is lit a little bit, right? Ignoring shadows and stuff, there's a base level of lighting applied to the entire area. That's going to be your ambient lighting. Your diffuse lighting takes into account like the direction of the sun. So it will say that anything that's not facing the light source, we'll call it the sun, is going to be darker than anything kind of facing the same direction as the sun. And that's what you see here. Specular lighting is when you're looking, if you take an object, a shiny object, and you put it at an angle to a light, you'll often see like a highlight on your object, which is called the specular light in this model, which basically means that it's the bright spot where any like shininess would be seen on the object. So you can see that in these 3 models separately, and combined you'll see that there's a base level of lighting which has a color and a brightness. Then you have the diffuse lighting added on top of it, and a specular lighting added on top of that, which gives you your combined model that looks like this, right? So if we go back to our code, I'll show you what I have right now. So it's going to look a little bit different because I've been doing my assignments with this thing. But you should have come up with similar code to this when you were doing your assignment in the end. And actually, we're going to be working with this specific object so we can see what it looks like. So this is the object I'm working with now. It's just a sword built out of a bunch of different pieces, and we're going to add lighting to this. Now I'm going to re-enable the camera to show you a couple of things. So in here, I think it's towards the bottom, I've got a line commented out here. This disabled the camera. So you'll see here, now we can move our camera. And if we move in, if we go into this sword, you can see it quickly. You'll see that the sword actually disappears when I'm inside the camera. And you can see it a little bit while it's turning. Now, the reason this happens is because I've turned off drawing the back faces of this camera. So I'm actually going to go into my sword. I'm going to make it stop rotating as well. Find my update method, update. And we'll turn off the rotation, and I'll turn on the setup window, open window. That's where it is. Turn this off here, and we'll go look at these again. So now you'll see same thing. You'll see the sword come up. I'll move into it, and you'll see that as we move into it, when we get inside, you see that you can see the yellow side while you're in the middle, which we couldn't do when we had the back face culling when we had the backface culling enabled. So backface culling, what is it and what does it mean? So let's just delete this. So let's just say we have a triangle, right? Now by default, OpenGL will draw both the front side and the back side of this face, right? So it will draw this side, and the side on the other side over here, it's also drawing that. Now what we want to tell it to save on resources is the biggest reason, is that because while you're looking at an object, generally, especially like a solid object like this one, like these ones, the meshes, you're not going to be spending time inside of the object. And even if you were, you don't want to be able to just like see, like, let's say the guts of a person, right? So you want to tell it to disable the backside of the object. Now remember, when we were defining our vertices with our cube, we defined them in counterclockwise order like this, which I said was basically the standard, but you could choose to do it clockwise, but you should make sure it's the same for all your faces. Now, when we built that cube, and the code that I gave actually had some errors inside when it came to this. I'm not entirely sure why it was the case, but when we enabled, so I'll do here, we'll go to our shapes just to show you what I meant. If we take our rendering, not core, game objects, it's in types? No, it's in core? Yeah, it's in core. I also refactored all of these folders, so don't worry about the structure. You should have an idea of how things should be organized, and you should work on, again, I stress that you should work your own style. This is me putting a little bit more of my own style inside here. I've separated things out into folders. That makes it a little bit easier for me to work with. So I've got the easiest one will be cube. If we go back to the cube, and let's just say, where's my cube? Cube. This is building this cube vertices. All right, here's my cube. So here, if you look here, these were our element buffers. Now, if I change this to 3.1 like this, you'll see that in this case, it doesn't look any different, right? But what we want to do is we want to tell it that we want to only draw we'll tell it that the front face of our triangles are defined in counterclockwise order like we did here. We'll tell it that we want it to cull or not draw the back faces of our triangles, because you could also tell it don't draw the front faces. And then we will enable the feature to cull faces, and that's what the 3 lines of code do. GL front face, GL underscore CCW counterclockwise, GL cull face, GL underscore back, which means cull the back face, and then you enable the feature by calling GL enable GL cull face, similar to how we enable the depth test. Now, if we run this again with the change I made to the cube, we should see, assuming I did it right, that you can now see that one triangle on all of my front faces is no longer being drawn. And that's because now that triangle is defined in clockwise order. And if we go to the other side here, you can see that, sorry, you can see that if we go to the other side now, in here, maybe not, it's bad, it's difficult to see. Here you go. So you can see that one side is defined on the right side, and if we go around, the other side is here because they're defined in the wrong way. So that should be your first step that you want to do this week, is you want to enable back culling. This is inside the GL, the open window function in my application class. I put it at the end after I've enabled OpenGL with the GLAD loader. We enable all of the back face culling. And what that will do is it'll expose to you any triangles that might be in the wrong order. When I enabled it, I found a few both in my pyramid that I had made and inside the cube that I had made, and then I spent a little bit of time fixing it. Now, There's a couple ways you can fix the issue if you find it. You can do basically what I did here. You can find which triangle is not being drawn, which could be difficult in some cases, but you should learn to figure it out, especially on these simple shapes. You can switch the element order like I did here, or if you notice that a big portion of so if you notice that, let's say this corner here, right? Let this corner between the gray and white, gray and red, I should say. All triangles connected to that corner are not in order or are not displaying. It's likely that that one vertex is the problem and you've put it in the wrong order in here. So like, let's say it's here, you see that, well, I mean, each one will have their own, but if you see that, you can also switch these, which works the same as changing the elements, but logistically, the way I defined these vertices, logistically in my own head, makes sense to me, so I can find them again more easily. So I usually prefer changing these out, but you know, your mileage may vary. You just need to swap some vertices around to make it work. Now we can get into actually doing some lighting. What I highly suggest that you take your time right now, turn this on before moving forward at all, because this being broken can cause a lot of problems moving forward. All right, we got that. I'm gonna give you 5 seconds so you can pause it and then you can come back. So 5, 4, 3, 2. All right, let's move on. So the first thing that we're going to do is we're going to implement the ambient lighting, which will be the base amount of lighting in our scene. And actually, before we do that, we're going to make a convenience function in our mesh class. Do we want to? Yeah, I'm going to make another constructor here. And what this is going to actually take, it's also going to take a DLM vec3, and we're going to call this, or let's make this const DLM vec3 reference, and we'll call this color. Now what this is going to do is that before actually uploading the data to the mesh, let's move this up, we're going to we're going to override the color of the mesh, just so that you can color everything in a way that makes sense for now, because we're not using textures. At least my shapes at the moment are not using textures. So we're going to use colors to make sure that the shading is working correctly. And it's going to be much easier to see if the shading is working correctly if all your vertices for your shape are the same color, because then you can see the shading properly. If they're different colors, it might be difficult to tell. Hopefully you kind of understand what I mean. So all we really need to do here, so first thing we need to do, we're going to go through every vertex. So auto reference vertex in vertices, and what we're going to do is we're simply going to say vertex dot color equal to color, like that. Very simple. And actually what we're going to do as well is we're going to this thing here, we're actually going to change into an init method. So we're going to say init vertices elements, like this. And again, we're going to do the same thing here, vertices elements. And we're going to make a function void init should vector vertex reference vertices should vector uint32t and elements, and we will paste that into here. There we go. And we need to make this a mesh like this. And this, it will be a private function, so I'm just going to move it to the bottom. And I will also change here indices to element, because I'm trying to keep the naming consistent. And then inside our mesh.h, we'll rename this elements. And again, I did this up here too. We'll change that to elements. And here we're going to have a private function, which will be void init and it will be the same parameters as this. There we go. Now that should resolve, no problem. I'm going to assume it does. Yeah, that all resolves okay. That's good. Now for our sword, which we're using as a model, I'm just going to go in quickly and change all of these mesh here where I create the mesh. Where do I create the mesh? Create hilt. All these meshes that I'm creating, I'm actually just going to make these GLM Spec 3. We're going to make it all we'll make it a gray color. Just a halfway gray color for everything. And we will just go through and add the color to these, create blades. That's the make shared mesh, make shared mesh, make shared mesh, make shared mesh. All right. Now another thing we did here is in the hilt, I also added a texture, I believe. Week 3, these are shaders, texture shader, models in place. We're going to put the week 3 shader here. Just to make it consistent. And now if we play that, we should have a pure gray sword, which will give us a pure gray sword. Now you'll see here, so what we're going to do here is now we got to add the lighting. That's why we used different colors before to define the shape. But now we will use lighting so that these shapes look correct. So first thing, which is not going to solve the shape issue, but is going to give it a look, is going to be the ambient lighting. So we're going to, in our application class, go here. It's in our core application.h. So we're going to say, we're going to have some light constants here, and we're going to possibly, I should say, make these configurable later, but we'll put these in here. So we're just going to say float, lighting variable. So we're going to put a float, ambient strength, make that 0.1f. Yeah, we'll initialize it to 0.1f. So again, you can make this customizable. And you're going to want a light color, which will be GLM Spec 3 light ambient light color. Now we'll likely make this more so the ambient light you usually don't want to be, yeah, this is going to be the color and this is going to be the strength. So we're going to make it a basic white ambient light at 0.1f strength. And what you're going to see, we'll put this in the shader now, and we'll see how that works. One thing maybe that might help you, I made a change in my CMake list. I might cut this out of the video, but if you look at my CMake list, I've created a new custom target called copy assets, and I've added the copy directory command to that, and I've added this custom target added as a dependency to my, I've had my project, my main project, the showcase app, the executable here. I've added to it a dependency of copy assets so that whenever I go to build, it will depend on this copy assets, which will just make it so that this runs every single time rather than having to wait as for the project to rebuild. So I won't have to do any small changes to the application in order to trigger the copy. So we're going to take this texture shader that we used last week. Actually, we're going to use this week 3 shader as a base for now. So we will call this week 6. We'll call this basic lit.frag. And again, we will call this basic lit.vert. So these are exactly the same as each other. Now in my sword here. So I call this week 3 shader, but I can call it, I can just do basic lit now. And here we will rename this to basic lit shader. There we go. And after we're done, we're going to combine the texture shader and the basic lit shader into one, so that we have one shader that can do everything pretty much. Okay, so we've got our basic lit shader. Let's just make sure that it runs by hitting play. And again, I do this every time. I make a small change that could possibly break things, and I double check to make sure it's okay. All right. So what we just did before is we had an ambient light and a ambient strength. So let's just simulate that here. Ambient strength equals 0.1. And then vec3 ambient color is going to be light color. So vec3 light color, we'll say it's white. So it'll be equal vec3 1.f, 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 like that. And then the ambient light itself, the ambient component, will be the ambient strength times the light color. And then finally, we get this vertex color. So usually you would have, let's say, it would be like, you'd have vec4 object color, or vec3 object color is equal to vertex color, and then, or like all the texture stuff here. So it'd be like texture, whatever that we did inside there. So we'll just do that. We'll have object color here. And we will actually just take the XYZ here. And then our object, this will be a vec4, or we'll say vec3 final color is equal to vertex color times light color, or ambient, I should say. It should be object color times ambient. And then here it would be a vec4 of the final color and 1, like that. So if we do that now, you're going to see that our scene will just have gotten much darker, right? And that's because the ambient color there's an ambient lighting added to the scene. So let's say there's no lighting in the scene. We turn ambient strength down, and we're not going to be able to see anything because there's no light in the scene. So that's the idea. So we'll keep that. So now that we got that out of the way, we're going to set up a thing. So we're going to leave this as a constant here, but we'll likely be attempting to pass this in later, right, as a material. But for now, we're going to leave it like this. So now what we want to do is calculate the diffuse lighting, which takes in direction. So remember, when we look at this picture here, let's say the light is over here. We want to take that into account and say that this side's going to be brighter than this side because the light's over here, right? So for that, we're going to need to put a light in our scene. And that's going to be pretty simple to do. First thing we're going to do to make it very simple on ourselves, we're going to make a new shader. And this is why I have this set up the way we do. Let's make it, we can actually use this week 3 shader. So we actually don't need a new shader because this has a color here, and we just need the color. So let's just, we'll rename this week 3 shader to be basic color shader, basic unlit color. And we'll do the same thing for the vertex, basic unlit color. And it's good to use good naming conventions here. So we've got our basic unlit color. Now let's create our light. Now our light, I have a game object system set up to be able to do this type of stuff. So I'm going to create a light here. It's going to be a C++ class. It's going to be snake case. We're going to call this light. It's going to be like this. This will be good. We'll add that to Git. We'll move this into our game objects down here. And then we will do some changes. Pragma once like this. Pragma once. We'll do include, and this will be game objects. Game object. So all of my game objects inherit from the game object structure, so that game object class, so that they all share the same thing. So I can have as many game objects as I want in the world and draw them in one call. You'll see me do that in a second. So with that done, we go to light.cpp. We need to change this here. Game objects light.h. And then we reload our CMake project. So creating classes, you should be used to doing it by now. That's why I'm skipping over all of the details. All right, so now we have our light here. It's going to complain that we haven't implemented. So you'll see my game object has an init, an update, a draw. We actually don't need the init, but we'll leave it there for now in case for some reason we need it. So we'll go into light here. There should be a generate here. Override functions. We'll generate all of them. Boom. Now we've got all of the functions we need here. All right. So how do I do my sword? Do I do it inside here or in my init? Where am I doing create shaders? I'm doing it all in my constructor. So we'll make a constructor here. So a lot of times in a lot of applications, you're not going to want to do, you don't want to do all of your creation stuff inside the constructor. And that's mostly because of a lot of times you don't necessarily want to create all the stuff when you have a in-memory representation, but I'm not worrying about that in this particular project. So I create my constructor, I move it to the top because that's where it should be. Now, basically, I'm just going to use the same type of model I used for my sword. So I basically, I'm going to have a mesh. Yeah, so I'm going to have various messages. So I'm going to make create shaders, create meshes, private, void create shader, void create mesh. So create shader. This is going to be, we're just going to do basically use the same code as my sword. We've used this before. We just create our shader like this. Light. So there's going to be another private here, and it's going to be standard shared pointer shader basic unlit shader. Now we're going to include, and I put this inside rendering shader like that. And I'm also going to need the mesh rendering mesh because there's going to be mesh inside here. And then there's going to be a shared pointer to a mesh, which is going to be the light mesh. Just literally, well, it's going to be a cube. So my sword has a model here, so we also need that in here because I've got a fairly again involved system. So core model like this. That should actually be in the header light. So again, you don't need to worry about setting this up. Just know that we're using a mesh and shader, and you can draw them directly inside your draw command. I've just got this model object here, which is what it does is it takes, where are you? Model.h, it's all in the model.h core. It's actually just a combination of the shader and the model like this, just so that I can draw the model, but you can have individual models here, which can have different meshes so that these game objects can transform them. See, they all have their own transform. So it makes sense in the end, but so what you're doing, what we're doing here is we're creating a cube in the scene that's going to circle the center of the scene around in the circle so that we can see the lighting change. And that's the point that what we're getting at here. We'll generate this as well. All right. So do I have models? No. So good vector model like this. We'll include, I've already included the core model. All right. So this should be fairly simple. If we look at my sword.h, sword.cpp, I should say, we create the shader like this. So I'll just copy this, go into my light, it's on my create shader. So it's going to be basic unlit shader, and that's going to be basic unlit color, like that, like this. So our shader is this one here, so we're not in our init. So here we're going to say create shader and create mesh, like this. Then the mesh itself is going to be created. Again, we'll use the sample code I have here. It's literally just going to be like this. We can copy this guard block as the best example. We'll go into our light.cpp. Guard block is like this. We want to include shapes, include for shapes. So I've separated it from our types.h into a shapes.h. And then we'll just say cube. And this is color. So our color itself is actually going to be pure white. And you'll see why in a minute. Pure white. And then we are going to models.inplaceback. And it's going to be cube, mesh, and then shader, basic unlit shader, like that. And then in our draw, literally I can just copy paste the thing here. Now you're going to see that my draw command takes in the view and the projection matrix so that we can set these like this. Now with that done, you're going to see that oh, I didn't add it to the scene yet. So I've got this light created. You can still see this sword a little bit. So with that done, we go into our application, and you're going to see in create or setup scene, I think it's called setup scene. I just push back a sword. We're going to do the same thing. We're going to push back, and actually we're going to capture it, and we're going to take the light like this, and we're going to make this a light. And we're going to here, game object, light. What? Why? There we go. I can use in place back to get a reference. All right. So you have in place back and our light, and we're going to move the light up. Light dot transform is equal glm translate light transform back 3, and we're going to, it's going to say, let's just say we're going to move it half a unit or 1 unit to the left, 1 unit up, and let's just say 1 unit deep for now. All right. Now what that's going to do is it should, if I did that correctly, well, I did do that correctly, but this needs to be much higher. And we'll actually say 5 and 5. There we go. All right, so it's pretty much where we want it to be now. So you're going to see here, the sword is in the middle, and we're going to have it do a circle around the object. But for now, we're going to leave it right there. And that will be our light. Now that we have the light in the scene, we can actually, we can take the light, and we're here. Let's just say when we create our mesh, we'll say auto cube. Oops, auto cube model, and we'll say cube model dot get mesh transform equal glm scale Might have to add that header, but it's going to be cube model dot get mesh transform we want it from matrix transform.hpp and what are the, and it's just a vec3, so glm vec3, and we're going to make it 0.5 on all axes, and this will just make it smaller overall. Okay, now again, when I go here, one thing I want to change here is maybe this is a little bit too far. Just to make it easier on ourselves, 2.5. It's going to be smaller, so it should be easier to work with a little bit. There, we got our light. So it doesn't need to be big. The white cube is actually just a visual representation of where it is. It's not actually going to be in the world in most situations, right? So since we have our model there, we have our light transform here. Now what we want to do, so what we need to do is we have this light inside the world. We need to send this light's position to the shader, right? So what we're going to do is we're going to do this in a little bit of a hacky way. It's not going to be a great way, but it's going to make it so that you can make light objects like this and have them work properly. So we're going to assume right now that there's only going to be one light inside the scene. So what we're going to do actually is inside our rendering section in our types, under vertex, we're going to create a struct to hold some information here for us. So it's going to be a struct scene parameters, we'll call it. Now the scene parameters themselves, there's going to be a few things. We're going to add our GLM mat for projection matrix. We're going to add our GLM mat for view matrix. And here we're also going to add a GLM vec3 light position. And we're going to say 0. Now, at some point, you're going to pass this in as an array to your to our shader, but for now we're just going to pass it in as a single one for now. So we do light position 0. Now what we can do, and actually we'll do uint 32p lights in scene. So this will be initialized as an identity matrix. This will be an identity matrix. This one will say there's been 0, and this one can just be a basic 0 matrix. So that'll be fine. Now in our game object here, our draw, instead of taking this, we're going to say we're going to take a. It's not going to be no longer const. It's going to be scene parameters reference scene params like this. And we will, and I want to do it with my angle brackets. Now we need to update each one of our dependent objects or child objects like this. Now the reason we're doing this is so that we can pass in the required light information into our shaders. Now the way we're doing this in realistic terms is not the performant way to do it. Usually you would update your light data as a uniform buffer to your shader, and you would batch your draw calls by shader type and by mesh type, so that you would have to do as little amount of these binds as possible. But you know, it is what it is right now. We're trying to keep this as simple as possible. So we change here scene params.projection, and scene params dot view matrix. This should be projection matrix. Projection matrix. There we go. And light scene params dot projection matrix. Scene params dot view matrix. Now the reason why I made it here is because we're going to do a little hacky thing where if it's a light, it's going to update its light data in the appropriate slot here. So if it's light 0, it's going to update the light position 0. If it's light 1, it'll go to, like, let's say we'll put this here now just to light position 1. And actually we actually don't even need this. We can just do lights in scene like this. So that basically the lights will upload themselves to the shader if necessary, if there is a slot left, a slot available for the light, if you understand. I'll show you what I mean. So in our application.cpp, we're going to have an issue now in here. So I'm just giving view matrix here. So now we want to build our scene parameter, which we can easily do just by doing scene parameter, scene params, and then projection matrix equal projection view matrix, that's comma view matrix equal view, like this. And we can just pass this into draw. Now the num lights is not going to change here. All right, so we are going to do this now. So we're going to create a spot inside of our, we're going to need to make some shader changes now. So the first thing is we are already getting the normals from the vertex attributes, but we're not passing them into the fragment shader, which actually needs these normals to be able to do it. So we're going to add a new out vec3 normal. And we're going to say not normal like that. We're going to say out normal, frag normal, let's call it. And we're going to just put frag normal equal normal, like that. And then inside our frag here, we're just going to say in vec3 frag normal. Simple enough. Text chord actually is not being passed in, and this is a, oh, we're putting this in the wrong, no, we want it in here. We're going to comment out this text chord for now because we're not actually using it. All right, so we have our frag normal. And that's how we get our normal data from the vertex shader to the thing. So we need another uniform inside our fragment shader here. So we're going to say here, uniform vec3 light position 0. And we're actually going to put another uniform light position 1. And this is just to show you what I'm doing here. All right. So that's simple enough. So, right. So this is going to hold our light position data that these lights are going to update inside their draw call. Right. So, sorry, I need to go back and change this. So we're going to go back to our types here. We actually do need these light position 0 and light position 1. And what we're actually going to do first, because we want our light to both be a game object and a light, right? So, because we need to process the lights in the scene before we process any of the objects, because the objects need that light data in order to actually do what they need to do. So what we're going to do then is we're going to, in our game object, it's going to be we're going to say virtual void. So this can be, the draw call itself can be constant now. I'm going to change that because I'm just changing the way this works. Again, we're going to fix these. It's only going to require changes inside the way we're defining everything. Now you're going to see why I'm doing this in a minute. This whole lighting thing is a little bit more complicated once you start abstracting everything out, but you'll see it'll work out. It'll be fine. Transform exists. Don't give me that. It exists. Okay, I'm just going to leave it. It's going to fix itself. Yeah, it's going to fix itself. I'm sure it will. All right, so inside our game object, we are going to just say handle process lighting, let's say. And this one will take the scene parameters like this. And this one's going to do what I was going to do inside the draw call. It actually needs to happen before that. So inside our light.h, we will refactor, generate override function. We're going to generate the process lighting function. We're going to do the same thing with the sword. Sword, generate, override, process lighting. All right. Now this is actually going to be very simple for the sword. For the sword, we're literally just going to return. We don't need to put the return call, but here. This isn't a light, do nothing. For our light here, we should actually move this up to be with our other public functions. I'll do it with my sword too, just to be consistent. Create hilt, create shaders, draw. There we go. Okay. So our light, what it's going to do is it's going to see first, it is a light. So the first thing we're going to see is and what we're going to do, we're going to say, we're going to make a constant expression, which is going to be an unsigned int. It's going to be a small one. It's going to be max light like this. We're going to say 2 for now. And here it's actually going to be a vector of DLM vec3s, which will be called light. And we don't need this one anymore. This it looks better. So it's just, instead of light and scene and those two variables, we're going to do this, and you'll see why I want to do that here. All right, give me 1 sec. All right, and then we also need to include vector here. All right. So now that we got that done inside of our light, this should fix itself. Oh, it should be std vector, sorry, not glm vector. Std vector, glm vec3. So inside our light, we're going to say if scene param dot lights dot size is smaller than max lights, which is going to be, so if it's 0 or 1, it'll be true, but if it's 2, then no more. So this will be good. Then we're going to add a new light. So we need the position of this light, just the position, not the entire matrix. So the matrix itself is this. So this is going to be the final world space transform. Std DLM mat4 world space transform is this, right? It's just gonna be the transform, so I don't need to do that. It'll be the transform. The light is going to be at the transform here. And then what we're going to do is we're going to get the position data from that transform and set it to lights. So we're going to say scene params dot lights dot in place back, and we're going to say, we're going to put this here. We're going to say light position. So the position of a matrix, of a transformation matrix in GLM is actually the final column of the matrix. So if we look back, let's see if I can find a good explanation here. So if you look back at how matrices are composed, this is our transformation matrix. Our translation, which is the position in space that our matrix is in, is actually the final component of this matrix, like this, right? So that makes it fairly simple. We can do auto. We can put it in the if statement. So we'll do auto light position is equal to GLM spec3, and we say transform, and we take the fourth column like that. And you'll see here that that's how we process the lights. So we put these lights inside here, and then we're done. So this will do that. Now what we need to do in our application.cpp is we'll have another model loop up here, which again, this is kind of inefficient, but we're going to say process lighting like this. So it's going to add the lighting data to the objects here, and it's going to draw it, right? Now that that is done, we've got basic lit, we've got our light position 0, our light position 1. Let's go back to what we need to do next. The final thing that we need is we need to know the fragment coordinate in world space. Now the fragment coordinate in clip space or view space, the window space, is what we get from frag color here, right? Vertex color, frag color, maybe not. We don't get any position. Yeah, so we actually don't get any position at the moment. So we have in frag color outgoes, we get the vertex color, the frag normal. We need the frag position, so the position in world space of the fragment that we're working on. So we'll put in our vertex shader, we will put one more out up here, out vec3 frag position, and this will just be it's going to be not the entire GL position like we did before. It's actually going to be this sub component here. So we want it as a vec3 like that. So what we're doing is we're just taking the position of the vertex and putting it into world space by multiplying it with our model matrix, and then we're sending that to our fragment shader. And again, we go into our basic lit and we go in vec3 frag position. Now let's before we continue expanding our view here like this, let's go in and actually upload this these light positions. So now that we've got we're processing our lighting, what we want to do as well, and again, a lot of this draw command here could probably be put at the game object level, but you see that there's a different set of models, so I need to be wary of what I'm doing with that. But since this is unlit, we'd actually only need to worry about our sword. So our sword here, what we want to do, you see we're setting the projection view in model, and if you look at our basic lit vertex, we got projection view model, but now we also want to do the light positions, right? So the way that works is we have a set mat 4 here. We don't have a set vec 3 in our shader, if I'm not mistaken. No, so we will add a set vec 3 here. Set vec 3 constant string string uniform name constant BLM vec3 like that. And then we will generate that. No, we will generate that function, not roll back that code. No, come on. There we go. Generate the function. We will put this with right above our set mat 4. Now, we do, it's going to be, first we want the uniform location, uniform location equal get uniform location, uniform name, just like all the other ones. If uniform location is not equal to -1. So, and then after uniform location, we're going to do GL uniform 3 float vector, and it would be uniform location 1 value GLM value pointer vec3. There we go. So with that done, what we can now do is inside of our sword.cpp, we can now, before we do, no, we want to do it for every shader. Now what we can do, no, we're not going to do it. Do we? Yeah, yeah, that's what we're going to do. So we're going to say shader last bound. I'll make the shader pointer, sorry. Shader pointer last bound shader is equal to null pointer. Now, if last bound shader not equal, if shader not equal last bound shader, then we will bind them and we'll re-upload the view and projection matrix, and we will also handle lights. So here we're going to say for auto light in scene param lights like this. What we're going to do is we're going to say we will say shader. Actually, we want to make this here. We will make this an int auto I equals 0, I smaller than scene params dot lights dot size, and I smaller than max lights I plus plus. And then we will say for the shader, we're going to say auto, we're going to say std string uniform name is equal to, it's going to be this. So we're going to say, we're going to do this a little bit. We're going to say light position like this, and we're going to say uniform name plus equal I. S2 I2 A like, we'll do it like this. No? To string. What was I looking for? To string. Standard to string I, like this. So this is going to take light position and add the index of the light to it. And then we're going to say shader dot set vec3 uniform name, and then scene params dot lights like this. There we go. Now we should have the light position in the scene as expected. Now let's just run that to make sure that everything's still running. It shouldn't be doing anything yet other than run. It should give us exactly what we had before with the white cube as a light and the gray here. All right, good. Now that that's set up, let's go back to what we were doing. So now that's done, all we really need to do is work inside this fragment shader. So we want to add the diffuse color here. So we have the ambient color, we have the object color, which will move up here to keep things organized. We want the diffuse color. So we're going to be doing some mathy things that I don't entirely know the root of. It's going to be, I'll give you a general idea of my understanding of it, but it might not be 100%. My explanation might not be 100% accurate. So first, we need to calculate the direction of the light in comparison to, yeah. So we need to calculate the light, the direction to the light from our current fragment inside this shader. So first, we're going to normalize the normal by just calling normalize like this, and this is going to be frag normal like this. Then we are going to calculate the light direction, which would be light direction, which is going to, we also want to normalize it because we don't want to know about the magnitude of anything. So we're going to take the light position 0 minus frag position. Now this is only going to be, currently is only going to work with the one light at the moment. We have a spot for a second light, but we're only using one at the moment, so we'll do that for now. Now we need to calculate the diffuse impact of the light on the object. Now let's move light color up because this will be different. All right. So to calculate the diffuse, we're going to it's going to be a float. It's going to be the maximum value of between the dot product of the normal that we just calculated and the direction of the light we calculated, and 0, 0. Now, so the dot product between two vectors will tell you whether or not they are will tell you whether or not something is in front of something else, or whether or not they're perpendicular or parallel to each other, or if they're facing opposite directions. Now, if I'm not mistaken, if the dot product is negative, then it says that the light, or the direction, or the angle between the two vectors are facing opposite directions, are not looking at each other. If the dot product is positive, it means that they're looking at each other. And if they are, if it's 0, it means that they're parallel or perpendicular. Probably perpendicular. Yeah, perpendicular makes sense. So yeah, that I think that's the math behind it. Let's just see. Yeah, so the dot product tells you what amount of one vector goes into the direction of a different vector. So if it's negative, they're opposite directions. If they're positive, they're same directions. If they're 0, they are going to be perpendicular. I believe 1 is going to be parallel. Let me just see, dot product parallel. It's going to be the product of their magnitude. We're taking normalized vectors. So when you take a normalized vector and you make the product of both of their magnitudes, it's going to be 1 because the normalized vector's magnitude is 1. Make sense? Hope it does, because I'm going to move forward now. All right, so then we have the diffuse, actual diffuse color. It's going to be vec3 diffuse. Oops, not big U's. We're going to diffuse equal to diff times the light color, like this. Now you see here I have light position 1, light position 0. These are actually going to be slightly different in a minute. These are probably going to be an array of light structs, which will have these defined as colors, but we'll get there when we get there. And finally, here where we have object color, final color, object color times ambient, we're going to move this to the front here. We're going to just do it doesn't need to be in parentheses, but just so you see, it'll be diffuse times object color. Now, in theory, if I did everything correctly, my normals might be screwed up, maybe. I can see it. You can see that's the hilt, I think. That looks like a cylinder to me. Let's make the let's make the ambient strength 0.5, just so we can see, hopefully see better. All right, so you can see now, you can see what's going on here. You can see that's working for the hilt, that you can see that one side is bright, the other side is dark. And down here, is not perfect, but it is somewhat working. So the issue we're having is if we look back to our shapes, I believe we did not define any normals for our cube. Now, instead of defining all of these manually, we're going to add a function in the constructor, the init function of our mesh class, that will calculate our normals for us. And the reason we do this is so that our normals will always be calculated for us, and we won't need to do everything by hand because we're lazy. So so you see my pyramid, I have some normals here because I actually took this code from a previous project of mine. But our cube, we never added normals, which we can actually guess what these normals are going to be, but I don't want to do that right now. Should we do that right now? Yeah, I'll show you basically what these should be, I think, just so you get a feel for what normals are actually doing. So let me just draw my cube. So I explained briefly before, and I'm going to make this a really ugly cube. I explained briefly before that normals are the direction, are the direction of the vector of the face on each vertex. So they're actually over here, the direction of the vertex for that face, right? So you have a face facing this way, a face facing this way, and a face facing out here. So basically our normals, we want to be able to basically do the exact same thing for each one of our faces. So for the front face, we're facing Z inwards, which I don't know. I believe that that's giving me, I think that was giving me, let me see, light here. I made the position vector of the light setup scene. I made the position of the vector positive on the z-axis, and that came inward towards the camera, right? So yeah, it came inward towards the camera. So we know that the front face, if we go back to shapes, there's shapes. Why can't I find shapes? Shapes. There they are. All right, so the front face is positive Z direction. So we'll say normal equal like this. Now, if we look at vertex, it needs to be in the same order. That's why I put it there. And this will be positive in the Z direction. So 0, 0, 1. And we're actually going to add them on every one of these vertices. Like that. Now, I'm just going to do it like this. This is the right face. The right face, if we look here, is pointed positive in the X direction. So cubes are very simple to do by hand, which is why I'm doing it by hand here. So positive in the X direction, and then 0 on the rest. Like that. The back face is going to be negative in the Z direction. 0, 0, -1. And the left face is going to be negative in the X direction. Normal equal -1, 0, 0. And then the top face is positive in the Y direction. Normal equal to 0, 1, 0. And finally, the bottom face is negative in the Y direction. Oops. Negative in the Y direction. All right. Now, if we play that, my cube should now show lighting, right? See that backside is not lit, but the front side is lit. Now we're going to change the clear color just so we can see my sword better. Clear color, that should be an application. Clear, GL clear color. So instead of this, we're going to make it a, I don't know, 2, 1, 5. 5. It's gonna be some weird color, but I don't care. This will make it so that we can see all sides of our sword here. All right. So you see now that my light is up here, and you can see that any part of my sword that is facing the light is getting lit, and anything that is on the back side is not getting lit. And you see here, and you can see here that my pyramid is clearly not working properly. See? Yeah, there we go. And you see as the sword, as we get further and further away from the light, the sword gets darker and darker towards its tip, and that makes sense. Okay, so now we're going to automate the production of our normals so that we don't have to worry about this anymore. So in our mesh class that we had before, I have it now in rendering mesh. We added this init function. Now before here, we're going to loop over the vertices here for auto and vertex in vertices, generate normal. So to calculate the normal, and we'll do this in Paint first so that you understand. So we need to calculate a normal of each one of our triangles. So let's take the brush, make it big. So our triangle is 3 vertices, right? Now to get the normal of this face, assuming that we're going to say that the whole face looks in one direction and there's no smoothing, what we're going to do is we're going to take this vector here of one point to another point, this vector from one point to a different point, and what these two vectors do together is they define the plane of the triangle, right? So the triangle is defined on a two-dimensional plane by 2 vectors, right? No matter which 2 vectors you do, they're always going to be on a 2D plane in some orientation. If we take the cross product, similar to how we were doing camera movement, if we take the cross product of these 2 vectors, we're going to get a vector that's perpendicular to the plane of the normal. So it would be like this. And that's the idea of what we're going to do. We're going to loop over all of the elements inside of our array, inside all of the elements inside our element buffer. And then what we're going to do is we're going to set all the normals for those elements, right? So this is what we're going to do. So first, we're going to define this function that will define the cross product here. So we're going to actually call update normals. So in our shapes here, we're going to make a static inline function. We're going to do it at the top here in shapes, static inline. And this is going to just be a void function that is going to update normals. And it's going to take as parameters 3 vertices. So GLM, it's just going to be vertex, reference, 0.1, vertex, reference, 0.2, and vertex, reference, 0.3. Now, what do we need to do? First, we create these 2 vectors that define the plane. So we want vector 1, which is going to be GLM, vec3. We'll call it U for no reason other than the fact that that's what I have in my reference code. We're going to take the second point dot position minus the first point dot position. And that's the first vector. Now the second vector, we'll call it V, is also going to be relevant relative to point 1, as you see here, it starts from one point and goes to the other one, will be P3 dot position minus P1 dot position. So remember, this is end position minus start position. End position minus start position is equal to the direction vectors. Now we want to take the cross product of those vectors, and that will be our normal. So we'll say auto normal equal to GLM, and we have a cross here, and we just cross the two vectors like this. And then we update all of the vectors. So P1.normal is equal to normal, P2.normal equal normal, and P3.normal equal normal, like that. And that is going to be how we update our normals on our vectors. Now what we need to do inside our mesh class here is go over every element 3 at a time. So instead of doing an auto like this, we're going to say auto I, or yeah, we'll say element, we'll just say I equals 0. I smaller than equal to elements dot size, and then I plus equal 3. So that's going to jump 3 at a time, and it's going to make it so that we can update our normals. So what we will say is we'll just say shapes update normals. Now this might be something we want to do inside, we might want to define this inside our mesh class as a static function. Maybe it might make sense inside of our types structure. I'm going to leave in shapes for now because shapes is more all over the place. So update normals, and what we need to do, and just to be clear, we'll say auto like this. We'll take the reference. You know what? We'll just do it like this. We'll do it directly inside vertices, and we'll say so here P1 index. Well, we do need the indices index is equal to elements I. Auto P2 index is equal to elements I plus 1. And as you can imagine, P3 index equal to elements I plus 2. And then we will call P1 index like this. And we can just copy this and do P2 index and P3 index. And that should, in theory, give us what we need, where it will update all our normals. Now, what we might see doing this, and we'll see if I'm correct on this, is that it will, the smooth, oh, what did we do here? All right. Vertices, P3 index, what? All right, what stood vector in it? Size, elements 384, I is 384. Oh, oops. It's not smaller or equal, it's just smaller than elements.size. New mistake there. All right, now that will give us, now you can see that still wrong. So what that tells you, possibly. So let's, now in our shapes here, let's actually go through and remove all of those normals we added to our cube, just so we can see if it is indeed doing what it should be doing. Normal, 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 normal. Oh, and normal, normal, normal. All right, oops. We want the UVs. Okay, now let's see this in action and see if that works. You see that the normals are still there. Now, why the pyramid, this pyramid, the lighting is wrong, right? So you can see here that the lighting on this, it should not be this color. So there's something wrong with my pyramid UVs, normals. So I want to make sure to see where the disconnect is happening. So it's something to do with this rotation. So you can see here that now that it's not rotated anymore, there's no issue. And oh, this one's all screwed up too. Yeah, it's screwing up because of the rotation. So I want to say that it's something to do inside here. Okay, so what we've determined is that any of these sword objects that have been rotated are not displaying our diffuse lighting properly. And the reason for this is because it's not taking the model transformation into account when doing these normals. Now what we need to do, I'll read directly off of Learn OpenGL and I'll actually bring it up just so you can see here. So the trick to fixing this behavior is to use a different model matrix specifically tailored for normal vectors. So this matrix is called the normal matrix and uses a few linear algebraic operations to remove the effect of wrongly scaling the normal vectors. So see, if you add a scale to the normal with the model matrix, it will screw up the normal as well. Now the normal matrix is defined as the transpose of the inverse of the upper left 3x3 part of the model matrix. Now, if you've taken linear algebra, which I believe is a prereq to this class, you should know what an inverse and a transpose matrix is. So in the vertex shader, there's actually the transpose and the inverse functions. So we're going to do that now. It's written right on this page that doing this in the vertex shader is actually quite expensive to do it for every vertex, because the model matrix will be for the entire model, not for it won't change per vertex. So what we need to do is normally we would calculate the normal matrix, the inverse transpose matrix on the CPU and send it over with these other things, but we're going to do it right in here to make our life simple. So we're going to take the mat3 of the top so we take the top left 3x3 matrix of the inverse transpose of the inverse of the model matrix. I know it's a mouthful, and we times it by the normal. Now, if we do that, in theory, we now have lighting that acts like it should. Now we have a beautifully lit sword from one side. Now, to demonstrate this working in real time and it being cool, what we're going to do is inside here, we have this transform here. What we want to do is we want to rotate it around these two. But we could just move it left and right or in and out. We're going to go into our light.cpp inside of its update function, which is here. And we're just going to say, we're going to put a float total time. And this is going to be very kind of a very simple function. We're just going to have it oscillate left and right so we can see the light update. So to make it oscillate, we're going to take the cosine, we're going to say float. We're going to say total time plus equal delta time. Delta time like this. We'll do that at the end of the frame. And then at the beginning, we're going to say auto cosine is equal to good cosine of total time. And auto sine is equal to good sine of total time. And we're going to say GLM no, it's going to be transform equal GLM translate transform GLM vec3 cosine 0 sine. Now that should make it oscillate back and forth if I'm not completely mistaken, because I've got it wired into these update functions. That's why I have this model. There. So where is it going? Where's the light? Where is the light? There we go. There we go. It's doing a pretty big circle. All right, so first things first, we are going to keep it in the middle like this. Keep it in the middle. And then we are also going to, in our light here, we're going to actually divide this by 2. Like that. So it should make a smaller circle. And now if we move up, move up, you can see our circle is still really big, but it goes through the, actually, let's do divided by 10. I want it to do a smaller circle, and I want it to actually circle the, there we go, smaller circle. It's still going through the origin, because that's where I've defined it to start. So on the Z-axis inside my application, I will put it back, let's say 2 units. I want it to actually go around the sword. There we go. So you can see as it moves forward in front, the back gets dark. As it moves, boom, beautiful. And if we follow it, we can see all the sides lighting up and changing. And that's how we do diffuse lighting. Finally, now we get to specular lighting. For specular lighting, what we want to do, and I'm just going to bring this up because I'm not going to draw stuff that's already drawn. So we have our eye, which is where the camera is, and we have our light, which is where our light is, right? Now, the specular is based on whether or not the reflection of the light is aimed towards the eye, and the specular amount is the how directly into the eye that becomes, right? So that's basically what specular lighting is. With that definition, you could imagine that what we need to do is give it the camera position to use as an input. So we'll do that as well. So we have light position here. We're going to put one more vector here, uniform vec3, and we'll call it view position, or eye. We'll call it eye position. Eye position. Now we need to set the eye position. So if we look inside our types, I believe is where we put it. Scene parameters, we also want, we can actually maybe get it from the view matrix, but to be very simple about it, we're going to say here, GLM vec3 camera position. We'll make it default to 0 like this. Then inside, with our camera position done, we also probably need to go to our camera because there is no get position here, right? Yeah. So we're going to add a get position, GLM vec3 get position const, and we can actually just define this inline return position like this. All right. And then finally, we need to send this to the shader. So in our draw function where we update our scene parameters, we will also add our camera position is equal camera dot get position like this. And then inside our draw function for our sword, specifically because it's the only one that's using the lit shader, we also need to set the camera position. Set camera position. So we'll say shader set vec3, and this will be eye position scene params dot camera position like that. And we'll just make sure that I call it eye pose. Yeah. All right, so we have our camera position going to our shader. Simple enough. Now we will add another section here. So we're going to add another float called specular strength. Specular strength equals 0.5. Then with our specular strength, we need to determine the view direction. So the direction from our fragment to our camera, which again will be normalized. So vec3 view direction is equal to normalize the view position or eye position minus the frag position like this. Then we get the reflection direction of that of the light. So that's going to be a reflect. There's a actual OpenGL function here called reflect, which reflects from the negative of the light direction, because the light is not going, you're not going to the light, you're coming from the light. So you want to negative the light direction. And then I believe you could just technically flip this around and you would get the same thing. And the normal as well, like this. Then finally, we calculate our specular amount. So similar to what we did with the diffuse lighting, we need to get the dot product between our reflect direction and our view direction to see whether or not they're the same light, or they're moving in the same direction, and by how much. So we'll start with that. We'll take the spec, and it'll be, we want the maximum, just like we did before, of the dot product between the view direction and the reflect direction, and 0.0. Right? So we do that. Now, from here, we want to multiply this value by a certain amount to determine how focused this light will be on the screen, whether or not it's so this, you can think of this as a shininess value. So if we say float shininess equal, we'll start with 32. So we want to do our float, we want to get the power of this dot product with the shininess, which will be our specular value. And then finally, the specular strength, and we'll move the shininess up here. And finally, the specular color for this fragment, specular, is the specular strength times the specular amount times the light color. And finally, with all that done, we add, so we actually did, so we did a multiplication here. So we actually want to do a plus here, not a multiplication, and specular like that. So actually, before we actually put the specular inside, I changed this to a plus. Let's press play. And you'll see that it's going to be a little bit more, yeah, so it's a lot brighter now. So that's why it was so dark, by the way. So when we did the multiplication here, when I had the ambient value as 0.1, it was taking all of the color values and actually multiplying them by 0.1, basically. So now we've got a nice lit up sword, and that looks good. Now finally, we will add the specular here. And we will hopefully be able to see that happen. So let's go inside here. So you should see, I don't see it. Maybe I'm going to change the shininess to 256 maybe. And I'm going to change the actual strength of this to 1, because I want to make this obvious to make sure it's working. There we go. All right, so you can see that as the light gets behind me and the reflection direction you can see that the reflection direction lines up with the camera, that we get the specular shiny value. So that's what this one here, we'll bring that to 0.5 and we'll put this back to 32. And that will give us a specular color. Boom. And you can see, I'll move a little bit closer so you can see it a little bit better. You can see that as it goes behind me, and you can see it as well. It might not look as much this way. You can see it happen for a second as well as it passes over there when it's ahead of me when I'm at this angle. And that's how you know the specular value is working. So now you have this cool look. Now I have this cool looking sword that has full lighting on it. And now to make it a little bit more complete, set up scene, just to make it look a little bit cooler, we're gonna move this up by 5. We're gonna also move this over by 2 to the left. Actually, we're gonna make this a little bit, we'll make it 5, 5, 5. And now hopefully what that will do is allow it to go around more smoothly. No, it's too much. 2.5 maybe. Boom. All right, cool. Now it goes around at around hip level and you can see the light going in and all that works. Isn't that amazing? So what we just implemented was a very simple type of what they call a point light, where the light is positioned somewhere in space, as you can see in here. So the light is positioned in space, and then light is created and reflected based on where that light is. Now, the proper implementation of a point light, if you look here, is that the further away that point light is from the object, and there's a limited amount of influence that a point light has, then the less influence the light has on the object. So that makes it so that currently what we have here, no matter how far the object is from the light, it will always have the same effect, which is why through the entire hilt or the entire shaft of this blade, the entire shaft of this blade is the same color, and because it's the same direction from the light and it's not taking distance into account. So what we're going to do is we're going to rename this light. We're just going to call it point light, and we'll revisit this point light later to make it better. Okay? Because what we're going to be working towards is having multiple lights in the scene. The next type of light that we are going to do, which is going to be a little bit simpler overall, is going to be the directional light. So we're going to have a directional light that goes in like this. And basically this will work similar to what we are doing now, where the distance to the light doesn't matter, but the light itself, think of sunlight, is always going to be pointing in the same direction. And since all of the rays of sun are parallel, it doesn't matter where the object is, it's always going to reflect that same direction. So that's what a directional light is. And finally, all right, so now that we have the point light basic set up, we're going to take a step back and we're going to move to just doing the various types of lights. So as I touched on, there is the directional light, which is what we're going to start with. And this is going to be we're going to call this directional light that there will only be one directional light per scene for somewhat obvious reasons. We'll call it, it'll kind of be like the ambient light for the entire scene, right? There's going to be one, it's going to be the sun, it's going to be coming from one direction, it's not going to move at all, and it's going to be like that. So what we're going to do is inside our scene parameters here, we're going to add one more struct, and we're going to define a new one. We're going to say struct directional light, and then the directional light itself is going to have a bec3, and we're going to call it direction. And one thing we're going to start doing from here is each one of our specular, diffuse, and ambient lights can have a different color on them. So we're going to allow for that inside these structures. So GLM bec3 ambient color, GLM bec3 diffuse color, and GLM bec3 specular color, like this. And here we're actually going to call these point lights like this. And these are actually going to, we'll keep them lights for now, but they're going to change in a minute once we get the point lights and we start putting them in there properly. So we're going to say camera position. We're going to add a directional light to this. And we'll say dir light here. And again, the direction, we're going to just initialize all these to the default, which it'll do it automatically without these, but I like being explicit, as you might probably know by now. So we have our directional light like that, and we will set that up inside our application.cpp. Now we're going to make this hard-coded, at least the value is hard-coded. You can, so in game engines like Unity and Unreal Engine, often you'll get like a slider to select the angle you want to go from. You'll have a slider to select the direction you want the light to come in from. But for our purposes, we're going to make it a constant. So we can do that. We can just do it in draw here, because we can just do it. So here we'll put in here dot directional light equal like this, and then we have diffuse. We'll have the direction, which is first. Now the direction, I'll just hit play on this so that we can get an idea. So if we assume that we want to shine the light, let's say directly forward, like here, like where it is when it's in front of the sword, like right there. So we want it to start, let's say at 0, and we want it to go down the z-axis negative. We want it to go, let's say we want it to come down a little bit from the top. So we'll say down the y-axis negative. And let's just say we want to go straight, let's just say a little bit to the left. So down the x-axis as well. So the way that we'll do that, so we want it to go, what we just said, a little bit, it doesn't need to be multiple lines, a little bit to the left. So we'll say minus 0.2f, 0.2f, a little bit downward on the y-axis. So let's just say it's minus 0.5f, and let's just say minus 1f like this. And we should probably normalize this. I don't know if that's going to be a requirement, but we might as well just normalize it now just in case. Maybe no. GLM, I should GLM 3 like this. All right, that will normalize a function like that. Then we want the light color. So let's just say we want a nice orange color. So there's a PDF file here that I like to use. I just searched orange and RGB normalized, and it came up with this PDF. So I just look through here for the color I want, which is, let's say we wanted a nice like daytime color, so maybe a soft yellow. here, maybe this one here. So we've got here. So I just copied that. It's 0.91, 0.7, right? So 0.91, 0.7. That'll give us a soft white color. And we are going to use the same color for all three. Now you might ask why we want separate ones. It's just because sometimes, for example, your specular color will actually, and a lot of times, will be brighter than your ambient color or your diffuse color. So so the ambient color actually should be smaller. So we'll put 0.1, and this will be 0.2, and let's just put 0.05, I guess, probably. So this will be a lot smaller, and then there's going to be some brighter things for the other ones. All right, we'll see how that looks. It might not be great, but we'll see. I'm kind of making it up as I go. So what we want to do is we want to add this to our shader. So for now, we will go into our basic lit, and we are going to make a function. We're going to put it here. We're going to put vec3 calc point light. And we're just going to put this code in here for now, which will point light, which is this here. And we'll just do that. And we'll return diffuse plus specular plus ambient, right? There. And we can remove this. So this is just so we can move it out of the way. Now we're going to put our directional light. So what we want to do with our directional light in our shader is we'll make a little bit of room. We're going to define a struct. We'll call it directional light like this, and we'll say vec3 direction, vec3 ambient, vec3 diffuse, vec3 specular, like that. And then we'll define a uniform of that type. Uniform directional light. This should have a semicolon. Uniform directional light, like that. Now, when we want to calculate our directional light in our shader, let me find it. So it's going to be exactly the same as what we had up here. So we'll actually just copy this. We'll copy all of it. It's going to be exactly the same as this, but light color, we'll remove light color, which will give us vec3 dir light color, and we'll say dir light color times opposite color, like this. Okay. So what do we need to change? We have light color here. This is going to be our dir light dot ambient color, dir light dot ambient, like that. Light direction, this is going to just become dir light dot direction, and this will be the diffuse color, so dir light dot diffuse color. And then our specular is same thing, we just changed the color here, so dir light dot specular, like that. Oh, and dang it. So I did it in the wrong spot because, here, let me just, I don't want to ruin the function. I just want to dir light color like this, and I didn't, okay. So I removed light color from here. So again, it'll be dir light dot ambient. Light direction is dir light dirlight dot direction, and the diffuse will be dirlight dot diffuse, and then the light direction has already been replaced, and then specular dirlight dot specular. Now in theory, I just need to upload the uniform for the dirlight here, right? So we have dirlight here. We'll go into our application inside of our sword like this. In our shader, we have this light position. We'll actually, actually, we can leave that there. It's not a big deal. But we want to set the dirlight direction. So it would be shader dot set vec3. So it'd be dirlight dot direction, and it'd be again scene params dot dirlight dot direction, and we can just copy this 4 times, and then so we have diffuse is equal to diffuse, and diffuse ambient equal to ambient. Oops. Ambient, and then specular is equal to specular. Now in theory, that should be everything we need to get our directional light working. So now you should see that we do have a light. Ignore the white one. So it's coming from the wrong direction. We want to change the direction it's going to on the Z axis. There, now it's coming from the front. You can see that the light now, it comes from one direction. And if I duplicated this sword, let's just do that so you can see. If I duplicated the sword in applications, scene, setup scene. So if I duplicated this sword, change this to an emplace back auto sword 2, and we want to translate this sword. So sword 2 dot transform equal glm translate sword 2 transform, and glm vec3 will move this let's say 1 unit to the right, like that. So it's not enough. We'll do 2 units to the side. We'll actually remove this light just so it doesn't annoy us anymore. And we're actually going to rotate this. We're going to rotate this by radians. We'll do it 45 degrees across around the y-axis, which should make it just spin vertically. There. So you can see that no matter where, which object is in the scene, that the light is coming from the same direction for all of them, right? So that you see that have that like soft yellow glow there. So if I wanted to, so let's say the ambient light we have that like yellow color, but if we go into here, let's just say the ambient light is not a yellow color, then you see it'll give it a slightly different look to the scene. So sometimes you'll want to have different, yeah, see now it looks a little bit different depending on what you look at. And see, you can see here, so you can see now, you can see the specular shine here because the light is behind me, and you can see the specular. So if we go back into our fragment shader and change our shininess to, let's say, like 128, and put this as 1, just to emphasize the point. You can see now that we got a much stronger specular highlight there, right? Now it looks like maybe like a ceiling light is reflecting off of the blade. So that's how you do your directional light. Now we're going to Spec 3 calc directional light. We're going to put all of that inside of this function. Here. Return dir light color. And now we're going to go back to calculating our point lights. We're going to add multiple point lights now so that they work properly. So we got our diffuse lighting in here now. What is this doing now? So dir light color is not there. So now we've got basically just back to what we were doing with no lighting at all, just plain gray. All right, so I hope you're keeping track. We'll actually move this calc dir light above to where the dir light definition is. Now the point light. So the point lights, as we showed before, they were really just directional lights with but with a position so that when they moved, the light would move. Which you can, which we could accomplish the same thing by having this direction and by using a position instead, right? But the point light, however, has will not affect things that are really far away from it, right? So as the light gets closer, it will affect the surface more, and when it moves too far away, the light will stop affecting it, because it's like, imagine like a small light bulb. In a dark room, it only goes a certain distance before there's no more light, right? So that's what we're going to be implementing here. So when we look at our here, so we got light.h, we're actually going to rename the file as well. Call this pointlight.h. Okay, that worked. And we're going to call this pointlight.cpp, and I'll reload this file. Just make sure that it still runs, because I might have screwed something up. Actually, I imagine that this still says, no, it's good. All right, so now, again, this got auto-imported, and it didn't give me my proper brackets that I like. So I'll hit that, and this should run just the way we were doing before. Good. All right, so now we'll go back to here. We'll go back into our setup scene, and we will add this light back, right? Now this light will continue to rotate, which is going to give us roughly what we want to see. So this is what we see right now. Now what we want to do for this point light is we are going to create another struct inside our types, which is going to make this more robust. So we're going to construct point light. This one is going to have a position. Actually, this doesn't need to be inside. No, it does need to be inside the parameters here. And then we'll need a GLM. So it's going to have the same 3 values here in case we want to distinguish them. And then we're going to have 3 values. So OpenGL has this in here. So it's called the attenuation distance of how far the light is going to affect. And it's based on this funky function here. Go to this website and read about it if you're really interested in how this works. But there's a quadratic term, and basically there are 3 values, C, L, and Q, if I read that correctly, and distance. Maybe not distance, but there's a constant, then there's linear, quadratic, and what is it? And constant. So the constant, I believe, is always 1. So basically, we're going to have these 3 here, which will determine how far and what kind of lights you want to have. And this table here gives you some values of some good beginning settings before you start playing with stuff. So we're going to use one of them from the table once we actually implement them. So this will have a float constant, 0.f, float, linear, 0.f, and float, quadratic, 0.f. Right? And now we want pretty much this exact same struct inside of our fragment shader. So we're just going to add that now. I'm going to reorganize this a little bit. We'll leave all the uniforms and stuff at the top. Actually, and we'll put the structure definitions near the top to at the actual top to make it just cleaner. Put the struct in here. Like you can see that, you know, this isn't, these things aren't actually. So we'll delete all of these. And we don't need to give these default values. There we go. So we have our point light, and now we want to create a uniform with this point light. So you see here we have light position 1, light position 0. So we're just going to put point light, light position, light, point light, 1, 0, and point light. Actually, we'll just stick with point light 0 because we're gonna be smarter with this soon. But we're gonna start with just implementing one point light. All right, now back to our application. We're gonna actually make this. Why is this not? Oh, inside of here, point light, point light. What? Redefinition of point light. Oh, there. Point light struct. And then here, actually, in our types.h, well, this will be point light struct inside here. All right, so that should have fixed the redefinition thing that was just happening. Yeah, all good. And this should fix itself as well. All good, 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 good. All right, so we've added the light. So when we, in our point light, in our process lights now, we're not going to do this. We are now creating this. We still need the light position, but it's going to be auto. That'd be point light struct, point light, like this. And let's do that. So first we have the position, which is going to be this, which we already have. And let's just replace that now. Like this. There we go. Now the next one will be, let's just check, it's ambient, diffuse, specular. So ambient color is equal to, we're going to say ambient color, because we're going to make these diffuse color is equal to diffuse color. And specular color is equal to specular color. Constant is equal to constant. Linear is equal to linear. Not quadratic is equal to quadratic. Like that. And now what we're just going to do, we're going to go here and we're just going to copy this and basically paste it into our pointlight.h in the public section. Now, usually you would use getters or setters for this, but because I don't want to, I'm doing it this way. And now we add the point light, and that will be the point light here. Then inside our sword here, where we're adding here, we want to set all of these uniforms. So we have set int. We also need a set float now, because we've got some float values. So we need a void set float const string uniform name float value, const, like that. You will, come on, come on. Come on, please. There we go. No, damn it. Come on. There we go. Generate the definition. Move it to underneath set int. We're just going to copy this because it's basically going to be the exact same function with the only difference being 1f, like that. Good. All right. So that's our set float, and now we can go into our sword and upload our light data. So the base uniform name is going to be point light 0, right? I think that's what we called it, point light 0. And again, it's gonna change a little bit, but I'm leaving it like this for now. And then we need to plus equal dot position like this, lights I, so dot position like this. Now let's just make sure that it's all capitals like I believe they are. Yes, they are. They all match exactly what I have here. So I can just do this. There's going to be 3 more. Diffuse color. Is it diffuse color or is it diffuse color fragment shader? Yeah, diffuse color. Let's actually make these consistent with the other ones. So this is diffuse color, ambient color, and specular equal specular color. Now we're going to copy this once just to do set float, and this is going to be constant, and will be constant, then linear, quadratic, and quadratic. There we go. All right, we're getting there. So we have, in theory, all of our light data being uploaded to the shader. Now we need to here actually set those values. So light ambient. Oh, get the game object. So auto this cast light equal to reinterpret cast point light get. That work? Oh, I don't need the there we go. All right. Now I can do cast light. Ambient color is, and I'm gonna use the same colors as I did down here. So ambient color is this one. Diffuse color is these ones. And this is going to be the same color. Specular color. There we go. Delete those lines. Now we set these constants. Again, I'm going to reference this table. Let's use, I'm going to do distance 30. The distance is going to be like 13 maybe. It's probably going to be less than 7. But I'm going to use 13 and see how that goes. So cast light dot constant, I believe it's supposed to be 1. constant is always the same. So, I mean, we didn't need to pass it in, but we're going to do it anyway because linear is 0.35. And then quadratic is 0.44. All right. Now all of the light data is being uploaded to the fragment shader, and we can add the point light. So this point light, we're going to do it actually inside of this function now that we have this working properly. So now what we need to do. So with this point light, we've calculated everything here. Now all we need to do really, yeah, okay. Now all we need to do is calculate that attenuation we just added. So we calculate the distance, which is going to be the length between the point light zero dot position minus frag position, like this. And then the attenuation is just that big equation we saw in Learn OpenGL. So it's 1.0 divided by point light zero dot position dot constant plus point light zero dot linear times distance. So it'll be, I'm going to put brackets here so you know the order everything's happening in. Then times point light zero dot quadratic times, and then this will be distance squared. Distance times distance. Like that. And then this whole thing can be multiplied by the attenuation. So we'll just do vec3 point light color equal calc point light. And we will say point light color times object color, like that. Now, if I didn't screw up, this should give us basically what we were expecting before, but a little bit more controlled. Okay, so you can see that oh, right, okay. So here, I actually did forget some stuff. Light color, we don't need. You can see here, I'm still using some old stuff, so I'll go through. Light color is going to be point light zero dot ambient. This is going to be point light zero dot position. This is going to be point light zero dot diffuse. This is good. And then point light zero dot specular. Now I think that's all that I'm missing. There we go. Now it looks like I'm too far away. So it is doing, no, it's not. Point light zero. Let's see what's happening here. Calc point light. So it's giving, this is coming out black. Why is it coming out black? We can try a different thing on this table, see if that makes any difference. So this would be 0.7 and 1.8. Yeah, 1.8. -1. So it's not finding the uniform point light 0 dot position dot position dot diffuse. What the fuck? Well, that's weird. Okay, so it is doing something weird. Oh, there. Okay. I'm doing a plus equal here for whatever reason. For whatever reason, I accidentally put a plus equal here. So let's try that again. Let's just make sure that this is resolving properly. Are we getting anything? Yeah, so you can see now. So it's subtle, but boom, you can see that it is lighting as it passes by. So let's go back to here and put these back to the other values. Now they should light up from further away now. Yeah, so you see now that it lights up from further away, and let's say we want it to I'm trying to find a good value so that you can see it 0.45, and this will be 0.075. There we go. Now you can see a beautiful point light that's working exactly as we expect it to. All right, so this is good. Now, what we want to do, and this is what we're going to do, is inside our types, we have this max lights here. We're going to change this to max point lights. We're going to say 4. Now, we are going to do the exact same thing here. Give me a second. In our shader. All right. So we've got our point light and our directional light. Now let's make them work together and also make it so that we can have multiple. So the first thing we're going to do is to have multiple point lights. We're actually going to do this. We're going to define max point lights like this. And we'll call this point lights. Now, to make this work, what we're going to do is we're going to loop over all of the point lights, and our calc point light here will take in a point light. It's going to need, we're going to take the normal, so vec3 normal, and it's going to take a vec3 view direction. Right? So now, everywhere that we reference a point light 0, we'll put light.ambient, light.position, light.diffuse, light.specular. Right? Then where we get our normal, we will actually take this out, and we will just replace that with the normal. And our view direction, we can just leave like this, right? Good. And now what we need to do is inside, we will add so we'll have a vec3 final color, or vec3 result, we'll call it. And we're going to say calc dir light. This is only one directional light. We can just do that like that. What we're also going to do, though, is we're going to take the calculation of the normal and the view direction out of here. So normal is here. We'll take this out. We're going to move this here like that. and we are going to move the view direction out like this, just to save on some calculations. We also need the eye position, so we can find eye position. Oh, that's already here. So we take that, and we're going to take the same functions inside here, and we're going to pass in norm and view dir here. So we start off by calculating the directional light. So we're going to loop over all of our point lights. So we're going to say for int I equal max point lights. I equals 0, sorry. I smaller than max point light. I plus plus. We're going to put a curly brace there. Oh, there should be 4. We're going to make 4 maximum point lights like this. And we're going to say result plus equal calc point light, point lights I, normal, and view direction like this. Right? Now let's see what this gives us, right? So let's just play that and see what happens. It's gonna fail, for one. I can tell you why it's gonna fail in a second, but we should be failing. Right. So what are we failing on? Norm undeclared identifier. Oh, in here, we want normal to be this, like this, and let's see if that compiles this time. Nope. Norm. Oh, so we normal, reflect direction like this, like this. 2 compilation errors. Okay, I got both compilation errors. So you make sure still unknown swizzle position. Point light 0. Point light 0. Oh. So here I've got a bunch of point light 0 calls. So point light. So we call light, 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 light. So let's try that now. And it doesn't compile. Point lights left of is not of array type. Point lights. Point lights. Oh, whoops. What is max point light? Is that the? Yeah. So that don't forget to actually make this an array of size max point lights. I forgot to finish that. All right. Now it's still not compiling. Point light color. Point light color. Oh. Sure. So it's not point light color, it's result times object color. There we go. Okay. So this works. Sort of. Doesn't look like it's getting the directional light properly. Because it should be at least doing the directional light. So let's comment out the point light and make sure that the directional light is working to start off. Directional light is working. All right. So we know that the direction light is working. Now we need to add the point lights in. And the problem with the point light is, I believe if we go to our sword here, where we're doing point light, we're actually not accessing the member of the array like we should be. It should be point lights, I believe. Basically, frag point lights. And then we want to give it the thing, and then like that. Now, if we do this, we'll just make sure that this is returning a uniform location, just like we were doing before, like when we debugged it last time. So, oops, in, out, in, out, in, and we have a uniform location. Perfect. So let's hit play on this and see what happens now, see if it's any better. Still not good. One thing I'm going to do is I'm just going to check to see if I change this to 1 and we only work with the one light, whether or not that, yeah, so the empty light data is causing an issue. So what I'm getting is that I probably want to initialize this. So what we're going to do here is when we go to our sword, we're looping here. We're actually going to go all the way to here. We're going to do a full loop all the way to max point lights. And what we're going to do is, so it'll be point light struct, light struct is point light equal, and then if it's I is smaller than scene params dot light dot size, then we will take this light. Else we are going to make it an empty point light struct like this. And then we will take the point light here instead of the scene param. And what this will do, and what this will do is it should initialize all of the data to 0 for all the lights, which should, if I'm not mistaken, fix our issue. It didn't. Right, so because this is doing 1 plus, so, oh, these are all 0. So I need to make this constant 1. All right, so the problem here is that the shader is actually crashing on this line because the default, all of this is resolving to 0 here. So to make that a default, can I give default value? All right, so you're not able to set a default value here. But since we, in our sword here, we have it here, we can add a default value here. And all we need to do is make this constant a 1 for our default value here. And now when we play this, in theory, this should work. Because it won't be dividing by 0 anymore, it won't crash, and it should give us what we want, and it should allow us to get multiple lights. There's our first light. Beautiful. Good. So there's our first light. Now, let's go back into here just to make sure that we're 4 lights. We're not divide. Oh. So give me a sec. Fix that. All right. 4 lights, turning direct color, and max point lights. Everything works. And we have default values being uploaded to the shader. There we go. Beautiful. And now we have diffuse and the directional light and the point light working. Now let's add another point light. So notice here we have a maximum of 4 point lights. So we can keep on adding point lights to the scene and basically get the same type of thing. So in our application.cpp, we'll find our setup scene. We have a light here, so we're just going to do it again. Light 2, cast light 2, change this, change that, change all of these ones. And now just to be extra, we don't want it here, we're going to make a nice pure red light here. With a we're going to give no ambient color on this one. So it's going to be a pure spotlight. And we're going to start it, I'm going to start it in front. I'm going to start it a little bit offset here. And we're going to make it lower, actually. We're going to make it, let's put it at 1. And make this at minus 1.5. Now we should have 2 lights that function. Nope, we had an error. What was our error? Let's see. So we go here, crash here, ambient, cast light to ambient color. Oops. We want light to dot get, like that. I think that's what we want. There we go. So we have a yellow light and a white light. That should have been red. Why was, oh, oops. And we actually want that lower now. Put that lower, and we'll actually put this one higher. And now we've got 2 lights. Red light. And you can see. Now, if we want to be extra fancy, we can derive from this point light and override the constructor, but that's not really needed for now. So anyways, with that done, excuse me, that's pretty much everything you need to light your scene. I know this video went even longer than all my other videos, it seems, but in the end, I think it'll be helpful. So what I would suggest you do after this, if you want to go a little bit further, so in this week's assignment, you're gonna, I believe you're gonna set, you might have to set up a spotlight, which we didn't talk about. If you go to learnopengl.com, you go to Lightcasters, Lighting, Lightcasters here. You will see down here, so we did directional lights, we did point lights, and we didn't, there's spotlights here. And then specifically a flashlight, which is basically a spotlight aimed where the camera is. And you'll notice that all the code that we used up here is very similar to what we just did without the multiple lights code. So you can implement your spotlight separately, or you can do the spotlight code, and then you can look at this multiple light section where it shows how to add like spotlights. So this is how our directional light, this is how we did our point light, and now the spotlight would go at the end here. And that's how it would work. So that is lighting. One thing I would look into on your own if you have time is uploading more materials to use as textures. Oh, that reminds me. Before we go, we're going to add textures back into this into our fragment shader. So we have our lit shaders here. We now want to take our textures inside. So we'll uncomment these things in our fragment shader with our text 0 and text 1. In our vertex shader, we still have it here. No, so we'll go into our texture shader. We want to out a text chord. So we will out a text chord, and we will just text chord equal UV, like that. Now, all we need to do now in our fragment shader, basic lit fragment, is sample our textures. So we're going to stick with a single texture for now, but I showed you how to mix them together the other day. So here we have object color. We want to take vertex color times, what is it, texture. We can just look at our texture shader frag, texture, text 1, text chord, like this. Text, well, it'll be text 0, text chord. Text 0, text chord. So it would be like this. Deck 3. Like that. Cool. All right. And that's all we need to add textures back. So just to show you, this will probably give us it'll give us our textures like this. So you see we've bound our textures. We have our textures on here. They're all being lit just like with everything else. So you see, goes around, gets darker, the light comes around. So let's not use that texture specifically this time. Let's go back to our sword, our sword.cpp. So you see that that's happening because when we create our shaders, we're loading Awesome Face here. Interesting. And we're not rebinding anything, so it's just taking the last bound texture. So what we actually want to do is we want to take this, we want to do this, remove this texture shader completely. Oops. And we will do this, remove this, basic lit. So we're just going to add the shaders. Now this uses all the infrastructure we had before. Now we should get the container images that we had before. Yeah, now it's the container. Just like that. Now with that done, we can change all of these to a white color so that we don't get texture colors interfering with our meshes. Like this. And same thing down here. Color, one color, one color, one color, one. And that will give us the exact textures specifically. There we go. Now you can see that red, there's red that shows up. And we have textures. And you can see it gets really dark back here because our directional light doesn't point back here. So it gets really dark. Lights come back here. You get the red light, you get the white light, and everything looks good. So that's everything you need to know to get through week 5, week 6. Week 6, we're on week 6 now. I don't know why I'm saying week 5. So hopefully that wasn't too much work and it wasn't too much information to dump on you, but going through all that yourself will give you a good understanding of how these lights and shaders actually get built. So with that said, I will come back possibly with some supplemental material, but you should have everything you need at this point to complete CS-330. See you next time.